Good morning, Year 12 specialist students. I'm going to go through our stuff for Digital Delivery Day now. I'm going to start out by doing linear substitution. I can't remember whether I did it the other day or not. I think we might have run short of time. So I'm just going to run through first. The lesson hopefully today won't be too long. If you can see here, we can always make a linear substitution because if I've got x minus 2, just going to get a skinnier pen. Okay, if we got x minus 2, du dx, if we let u equal x minus 2, du dx will just equal 1. So we can always just put a du dx wherever we want, because if I add a 1 in somewhere, like multiplied by 1, it's not going to make any difference, because we're not changing anything, because du dx equals 1. So in this case here, we say, let u equal x minus 2, therefore du dx equals 1, and we also know that x equals u plus 2. So we can make a substitution and say x, we know is u minus 2, no, we know x is u plus 2, so instead of x I can write u plus 2. Instead of x minus 2, I know that x minus 2 is u, so I can say u to the 5 on 2, and then we can just add in a du dx because we know du dx is just 1, and we're not changing anything, we multiply something by 1. Then from here, we can cancel them, the x's. So we end up with u to the, if I got 5 on 2, and I times it by u, I get to the 7 on 2, plus 2u to the 5 on 2 du. When I add 1 to the power, I get 9 on 2. So if I divide 1 on 9 on 2 is 2 on 9, u to the 9 on 2, plus 5 on 2, if I add 1, I get 7 on 2, and if I divide by 7 on 2, it's the same as timesing by 2 on 7. So I get 2 times 2 on 7, which is 4 on 7, u to the 7 on 2, plus c. Okay, from here, we know that that is 2 on 9. Oh, what was I going to say? We can take out u to the 7 on 2. So if I said u to the 7 on 2, what's left over? I've got 2 on 9, u to the 1, plus 4 on 7, and I don't need anything because I've taken out u to the 7, plus c, and we know what u is. We know it's x minus 2. So I'd have x minus 2 to the 7 on 2, 2 on 9, x minus 2, plus 4 on 7, plus c. The other thing we could have done is taken out a factor of, so I probably should have done it back here actually. If I wanted to, I could have taken out, let's make them both on 63. So u to the 7 on 2, 7 nines are 63, so it times the top by 7, 14u, sorry, plus, I've had to time the bottom by 9, so I get 36 on top, plus c. Okay, what goes into 14 into 36? 2 does. So let's say 2u to the 7 on 2 on 63, bracket. I've got 7. I've taken the 63 out, and I've taken 2 out, so I can say that's 7, u. And then, because I've taken a 2 out, that's going to be 18, and then plus c. But we know u is x minus 2. So I say 2 on 63, x minus 2 to the 7 on 2, 7 x minus 2 plus 18, plus c. And of course, 2 on 63, x minus 2 to the 7 on 2. I've got 7x. I've got minus 14 plus 18, which is plus 4, and then plus c. So that's our antiderivative. Yeah, so if we did that on the CAS, x minus 2 to the 5 on 2, x minus 2 to the power of 5 divided by 2. We want to integrate that with respect to x, and we'll simplify it. So 2 on 63, x minus 2 to the 7 on 2, 7x plus 4, which is exactly what we got here. So we didn't stuff anything up. Okay, in this case here, our linear part is x minus 1, so let u equal x plus 1. Du dx is therefore 1, so we know we can just add it into the equation. And we know that x is equal to u minus 1. So we can say that's not a u. It is 12:15 at night, so a little bit tired. X minus 1 squared on u to the half, because x we know is u minus 1, and we know that u is x plus 1, so we can say root u. And then we can add in a du dx, because it's just 1, and then dx. They cancel. So let's expand the top. U squared minus 2u plus 1 on u to the half du. When we divide it through, u to the 2 and u to the half is u to the 3 on 2. U on u to the half is u to the half. And then I get u to the negative half du. Okay, so when we integrate this, we add 1 to the power. So we're going to get 5 on 2, so 2 on 5, when I divide by it, to the 5 on 2, minus, if I add 1 to that, I get 3 on 2. So I'm going to get 4 on 3, because I already had a 2 at the front. U to the 3 on 2. If I add 1 to that, I'm going to get a half. If I divide by a half, it's the same as 2. So plus 2 u to the half, and then plus c. Now, if we take out u to the half, we're going to have 2 on 5 u squared, because that's the same as 2.5. If I take out a half, I'm left with 2, minus 4 on 3 u to the 1, so it's just u, and then plus 2, and then we have a plus c outside. I mean, there's no real advantage to taking out 15, but we can do it, and a 2. So I'm going to say 2u to the half on 15. So if I take out a 2, if I take out a 15, I've got to multiply the top by 3. So I get 3u squared. I have to multiply that by 5. So I'd get 20 on top. But because I've taken a 2 out, I'm going to get a minus 10u. And then here, if I want to put it on 15, that's going to become 30. We've got to take out a 2. So it's plus 15 plus c. And then we know that u is x plus 1. So I get 2 root x plus 1 on 15, 3 x plus 1 squared minus 10 x plus 1 plus 15 plus c. And of course you can expand that out, but I really can't be bothered. Okay, so this one here looks a bit confusing because I've got e to the 2x, and when I derive that, I get 2e to the 2x. But then we can't make a substitution. So if I let e to the x, when I derive that, I get e to the x. Okay, so let's try with e to the x. U equals e to the x plus 1. Du dx is therefore e to the x. But if we have a look here, we can get e to the x equals u minus 1. So let's try that substitution. We have the integral. Instead of having e to the 2x, I'm going to say e to the x times e to the x on e to the x plus 1 dx. Now I'm going to place one of these with du dx. So I'm going to say equals. I'm going to replace the other one with u minus 1. So I'm going to say u minus 1 on. We know that that is u on u. This e to the x, I'm going to replace it with du dx. So du dx. And then I still have my dx. So I'll just circle everything. So e to the x, we know is u minus 1. So I'll put that there. E to the x, we also know is du dx. So I'm replacing that e to the x with du dx. And then e to the x plus 1 we know is just u from this equation here. Now they can cancel. So I end up with the integral of u minus 1 on u du, which of course u on u is just 1, minus 1 on u is u to the negative 1 du. We know that when I integrate 1, I get u. If I add 1 to that, I get 0. So we probably should have left it as 1 on u du. Now we know when we integrate 1 on u that it's log e mod u and then plus c. So our integral is u, which is e to the x plus 1, minus log e of u, which is e to the x plus 1, and then plus c. Let's have a look and see e to the 2x on e to the x plus 1. So e to the 2x on e to the x plus 1. Let's integrate it with respect to x. So e to the x log e to the x plus 1, e to the x plus 1. U that's e to the x plus 1 and then plus 1. Now what they do sometimes, the calculator, see here how I've got a plus 1 and I've got a c. They say, okay, e to the x minus log e of e to the x plus 1 and then plus 1 plus c. They just say, well, if 1 plus c is a constant, so is 1 and so is c by themselves, but altogether we can say that 1 plus c is just the constant c. So here, when they do it in the CAS, they forget about like the value 1 because it can be considered to be as part of c, and you can just think of c like if I said e to the x minus log e to the x plus 1 plus c, if I wanted to, I could just say that 1 plus c is equal to d. So I could replace that with just a plus d. Either way, they're just a constant value, like it doesn't change. So the CAS will just get rid of that value. I'll explain more of that as we go along. Okay, so let's have a look here. We're using substitution, but we're finding definite integrals. So if we have a look here, my substitution is going to be u equals x squared plus 9. Therefore, du dx equals 2x. And from this, we know, because we've got terminals, they're to do with x, so we've got to convert them. So if u equals 0, if x equals 0, u is equal to 0 squared plus 9, which is 9. And then if x equals 4, u is equal to 4 squared plus 9, which is 25. So they're our new terminals. So as soon as we change over to u, and we've got a definite integral, we then have to go, okay, I want to go from 9 to 25. Now, 3x, if this was 3x here, what would we have to change it to? So if I want it to be 3x, I've got to times it by 3 and divide it by 2, which means I've got to times the other side by 2 and divide it by 3 to make it 3x. No. What have I just done? Okay, so I've got du dx equals, what did I say? 2x. So therefore, if I want the top, we could say a half du dx equals x, but I want it to be 3x. So if I put a 3x, I've got to multiply this by 3. So we can say, we can replace x with 3 on 2 du dx. So I can say 3x is 3 on 2 du dx. So that's that. The square root, x squared plus 9, well, we know that that's u. And then we've got a dx. So because we've put u's in now, and our terminals must be to do with u. Now that's constant, so I'm going to bring it up the front. So I'm going to say 3 on 2, 9 to 25. I'm going to say u to the half, so I've done that. They cancel. I've got u to the half, and then du. Okay, from here we know we've got 3 on 2. If I add 1 to the power, I'm going to get 3 on 2, which is 2 on 3, u to the 3 on 2, between 25 and 9. Now we substitute our values in. So 3 on 2. Oh, now if you think about it, because I've got a constant here, we can bring it out the front and make it easier. 3 on 2 times 2 on 3 is just 1, so we can basically get rid of them. So I have 25 square rooted and cubed minus, so that's what this is, square rooted and cubed. So that's our first term when we sub it in, minus 9 square rooted and cubed, which is going to give us, the square root of 25 is 5, 5 cubed is 125, minus, the square root of 9 is 3, 3 cubed is 27, so that gives us 98 square units. And to make sure we haven't stuffed it up, let's check it on the CAS. So 0 to 4, 3x, root x squared plus 9. Clear it all. Okay, so 0 to 4. I've forgotten it already. 3x root, well, 3x root x squared plus 9 dx. Okay, 98, beautiful. So we know we got it right. Okay, TK, are you listening? You don't look like you're listening. Okay, so next question. We're nearly done. Okay. We have got cos cubed x between 0 and pi and 2. Now, cos cubed x, we know that that is, let's make it bigger. So 0 to pi on 2, cos of x, cos squared of x dx. And we know that that's 1 minus sine squared. So 0 pi on 2, cos of x, 1 minus sine squared of x dx. So now we can let u equal sine x, because we know when we derive sine x, we get cos x. If we say let if x equals 0, u equals sine of 0, which we know is 0. If x equals pi on 2, u equals sine of pi on 2, which is 1. So when we make this substitution, we know our terminals are 0 to 1. You always keep, so that was the bottom terminal, so that's the bottom terminal, top terminal, so that's the top terminal. Even if they become negative or whatever, you keep them exactly the same order. We know that cos x is du dx. We know we've got 1 minus u squared, because sine is u, and then we've got dx. So that cancels with that, and we have got the integral from 0 to 1, 1 minus u squared du, which we know is u minus u cubed on 3, between 0 and 1. If we put 1 into that, we get 1 minus 1/3, and then we get 0 minus 0, which is, this here is 2/3. So let's check and make sure. 0 to pi on 2 cos cubed x dx. 0 to pi on 2. Now remember, when you want to do cos cubed, you've got to do cos of x all cubed dx. And we get 2/3. We're going alright considering it's 12:30 in the morning. Okay, last one. So here, you got to look for your substitution, and I think in this case, we're going to let u equal x squared cubed. So du dx is 3x squared, which looks very much like that. So if I want to make it a 2, I've got to divide it by 3 and times it by 2. Divide it by 3, times it by, it's going to get confusing. I'm going to put a dot for times it by 2. So here, I've got to say 2/3. So if I multiply it by 2/3, I know that this will just be 2x squared, which is what we want here. Okay, so I'm going to replace 2x squared with 2/3 du dx, and u to be e to the u. Now, if we let, if x equals 0, u equals 0 cubed, which is 0. If x equals 1, y equals 1 cubed, which is 1. Therefore, the integral from 0 to 1, 2x squared, we know is 2/3 du dx from up here. We know that e will be the same, but instead of being to the power of x cubed, it's to the power of u, and then we've got our dx. Now that will cancel with that. My 2/3 will go out the front as a constant. I shouldn't have done that yet. 0 to 1, because they're my terminals, they haven't changed, but you have to check and make sure if they do. E to the u du. Now we know when we integrate e to the u, we just get e to the u, because when we differentiate it, we just get e to the u. So we get e to the u between 1 and 0. So we get 2/3 e to the 1 minus e to the 0, which is 2/3 e minus 1. Now, assuming we haven't stuffed it up, what was it again? So, integral 0 to 1, 2x squared e to the x cubed dx 2e on 3 minus 2/3, which is what this is. Beautiful. So now you can finish off 7c, and you know how to do 7d. And if I can see that you've done that work, I'll come and check. I'll mark you there for delivery day. Digital delivery day. Oh, by the way, we got to stay home because the internet wasn't working. So I'm a happy boy. Have a good day. Bye.